Thanks for coming to this talk. It's a great honor for me to be speaking to you here. And thank you, the organizers, especially Roman and Martin, for bringing us all together. So I'll be telling you about real tropical geometry, principal minors, and matroids. I'll go over all these words. Yeah? So the new results in this talk, which will come in the last third or so, are based on this paper. It's on the archive. Joint work with my collaborators, Abia El Ahmadiyeh, Philippe Rincon, and Cynthia Vincent. All right, so I'll spend some time telling you tropical geometry. So if you have attended the pre-talk, you may have seen this, but we're going to review this again. Okay, so, sorry. Oh, yeah, okay. All right, this is for aimed at professors. Yeah. So I'm going to introduce this as a process that takes classical objects and that output a tropical object. Although, as you will see later, you can also like do some constructions purely in the tropical side as well, right? But for motivation, we're going to start in the classical world, like an algebraic varieties, which are geometric objects defined by polynomial equations. Semi-algebraic sets are they're defined by polynomial equations and inequalities over ordered fields. And then you get out some, oops, I erased this, about piecewise linear object, polyhedra, right? In particular, for example, if you input a curve, you might get graph, and then some algebraic operations become tropical operations where addition is maximum and multiplication is addition. I understand that in Kevin's talk, addition is minimum, but it's okay. You insert the negative signs at appropriate places and rotate the pictures 180 degrees, it's isomorphic, right? So yeah, the upshot is that, it turns algebraic geometry into combinatorics. So one origin of this is this paper by Bergman from 1971. So called logarithmic limit set of an algebraic variety. And then he's working over the field of complex numbers. And then, so you have a subvariety of this right here. You take the complex number, you throw away the 0 to the end, right? So this algebraic torus. Subvarieties means something defined by algebraic equations. And then they want to study the exponential behavior of the variety at infinity. So what they do is they take this absolute value, which is like complex modulus, and then they do some kind of rescaling so that my point, right? And then you take the logarithm and then you do the rescaling so that my point is on a sphere, right? On a unit sphere. And then look at all those points and look at some kind of a limiting behavior. So right here, we're going to look at, instead of, we're not going to do this rescaling to the unit sphere, but otherwise equivalent construction of tropicalization via logarithmic limits, right? So right here, I start with some set. So either algebraic or semi-algebraic set over C to the n or R to the n. Okay, we're going to throw away 0. This is what happened, like the star here. That means that I'm just ignoring the 0 coordinate because I don't want to take logarithm of 0, right? And then what we do is you take for each coordinate of the point. So you take a little, a point in my variety or semi-algebraic set. You take the absolute value, and then you take the logarithm base t, and then let the t go to infinity and see what happens. So let's look at this example. So there's a line in C2, right? So the real part is this line right here, okay? But it has a bunch of complex points as well. First, you take the absolute value. So this real part gets folded into this part. And then the complex points go inside. So that you can easily prove this using triangle inequality. The complex points have to land inside. Okay, so you have this. And then let's take log base t, because this object called amoeba. So let's see how to understand this one. Say the points that are important are the points around this point right here. This is when x gets really close to 0. That means that its logarithm goes to 1 minus infinity, right? So this neighborhood here goes to this infinite ray, and this neighborhood around here, y gets really close to 0. It goes there. And then points in that direction up there, they go to that direction over there. So you get an object like this called amoeba. Right? So amoeba also shows up in people's study of functions in complex variables, for example. And it's an interesting problem in itself to actually try to understand the amoeba. Like it has nice properties like the complements of these regions of the convex set. And I think so. For example, Torsten Theobald here is an expert in trying to understand this amoeba of algebraic varieties. But here we're going to take one more step after amoeba. So we're going to take the limit as t goes to infinity. Oh, I keep doing that. Right. So by the change of base formula for the logarithm, that means that you are dividing. Right? You're taking this set and you're rescaling it. You're dividing by larger and larger and larger numbers. So you're zooming out and zooming out. So that means that at the limit, you end up with these 3 rays. Okay. So let's look at another example. So right here, this is just a single line. But you can also look at a family of things, a family of curves right here. So right here, I'm thinking of t as a parameter, like I say, real number. Right? And then I could play the same game, and then this t is the same as the base of the logarithm, right? So the reason I might want to do it is that if I just do a single thing, yeah. That is because min and max, right? So it's a choice of signs. Yeah, so it's isomorphic. Yeah, great question. So you could use t goes to infinity, t goes to 0, then the picture I'm going to get, right, looks like this instead. Yeah. All right. So yeah, if I just have a single thing, then everything sort of like shrinks down to the origin, and you have a bunch of things coming out from the origin, right? So if you want to sort of differentiate things around here, what you have to do is look at a family of variety instead of just a single variety. So you have this family, so that things don't shrink all the way down, okay, because it's the same t as the base of the logarithm. And when you draw this picture, this is the amoeba for t equal 2, amoeba for t equal 5, t equal 50, and you can see at the limit, you get this piecewise linear object, right? So in general, you can say, what do tropicalizations look like? So for algebraic set or semi-algebraic sets, your tropicalization is always a polyhedral object, like this one, for example, right? So it has it's piecewise linear, defined by linear equations and inequalities. And then over C, things are a little bit nicer for algebraic varieties over C. So Beery-Groves theorem, which I think one of these people was in Frankfurt. Yeah. And then it says that this tropical object had the same dimension as the algebraic variety. And then satisfies something called the balancing condition. So it's like this one. So that means that there is a natural way to assign numbers to these points in the tropical varieties. So that, for example, if I look at this point right here, if I add up the rays here, weighted with the appropriate weights, they add up to 0. Okay, so it satisfies the balancing condition. You can also see this in our picture up here, right? So things look sort of balanced around each of these nodes here. Right, so this is what tropical variety looks like. So I'll go over some motivations why you might want to tropicalize things. So starting in the 1980s, so Vero had this thing called patchworking, where the goal is to produce algebraic curves with prescribed topology. So we know that smooth, plane, projective, real curves, right? Topologically, is a collection of ovals. And the Hilbert 16 problem asks what are the possible configuration of ovals. So you can use this Vero's theorem is that if you can construct this tropical picture with this configuration of ovals right here, you can see this piecewise linear ovals, then you can construct an actual real algebraic curve with the same topological configuration. So this is one motivation. So you may notice that these do not satisfy the balancing condition because we are looking at real versus complex. Okay, real things do not need to satisfy balancing condition. All right. So another motivation is 20 years later in the 2000s. So McHawken had this what he called correspondence theorem. So in enumerative geometry, people want to count the algebraic curves with prescribed degrees and genus that go through a certain number of points in general direction. So the number of points is chosen so that the answer is finite, right? So these answers are called Gromov-Witten invariants. So McHawken showed that number of the solution for the classical problem is equal to the solution for the tropical problems, and the tropical objects are much easier to count. So this way he came up with new formulas that were not known before. Right, at the same time, Ben Stromfels. He was using tropical geometry in computational algebraic geometry. So his idea is that you can, if you want to solve computational algebraic geometry, you have a bunch of polynomial equations in many variables, many equations and many variables, and you want to solve them. So he said, well, let's look at the tropical picture. Let's solve them tropically first. So in this case, on the left, you see the two tropical curves, right, meeting at 3 points. And then he can use these tropical solutions and do some things, for example, a numerical homotopy method, for example, and sort of guide you to the complex solutions. Okay, so this is one motivation. So yeah, so the story is that Stromfels and McCulkin got together in 2002 and then coined the word tropical geometry. Before that, there was tropical algebra for max plus algebra. That was the French people used to honor a Brazilian mathematician who worked in this area, who worked in max plus algebra, Imre Simon. Right. So I'll list some other things that, some other motivation that people look at tropical geometry. So we've talked about enumerative geometry and computational algebraic geometry. So today we'll be looking at matroid theory. So that is Alex Fink is here. He has some interesting, many interesting things in relation between tropical and matroid theory. And then Rincon, my collaborator, Jun He, for example. Right, and also some other local experts in tropical geometry, include Annette Werner and Martin Ulich. So they looked at non-Archimedean geometry, and also in more applied stuff, we have applications economics, celestial mechanics, or optimization. Right? You can ask me about them later. I will not go over them right now. Right. So now let me go back to looking at tropical geometry more closely. So what does tropical variety know about the original variety? Right, I already said that it knows about the dimension in the complex case. Right, in the real case, you get a bound on the dimension. But let's look at this another example. Okay, so let's look at this amoeba. So what do these infinite rays in these amoebas? What do they signify? As we have seen, you know, these rays, for example, this comes for the neighborhood where x coordinate is near 0, right? Near this point. So this tells us that, you know, it will, my arrow curve crosses the y-axis once, right? And then these two rays right here, or the multiplicity 2 in my limit, tells me that it crosses the y-axis twice here. Okay? And also, you know, this infinite rays tells you in which direction my variety goes to infinity, right? So these two asymptotically, they go to the same direction. So goes to this direction logarithmically, and then these, right, are seen by this direction, right? So in particular, tropical variety sees the behavior of my variety near 0 or infinity. So let's look at a special case of a linear space, right? So in a linear space, so like in this picture, my variety is the say that again. You mean like these? Yeah. Oh, why is there only? Yeah, in some sense, they go to the same infinity in some sense. Yeah. Yeah, so that is a little bit of a coincidence in that they go to the same infinity. We can talk more about it later. Yeah, yeah, that's right. Yeah, so in the linear case, right? So my variety in this case is the gray plane, and then what tropicalization sees things near 0 or infinity. In particular, it sees how the coordinate planes, right, restricted to my linear space. It sees like which of these coordinate planes, you know, which of these coordinates vanish at the same time or not. Okay, so it sees this middle picture right here. This is the picture of the 3 coordinate planes restricted to my linear space. Okay, so this sees a hyperplane arrangement, right? So in other words, it sees the matroid of the linear space, and I'll define that in a bit. So this is a tropical picture. So this was observed by Stromfels. and made it more precise by Ardila and Clivens in the early 2000s. So in particular, if L is a row space of a matrix, then the matroid of L is the information, is the data about linear independence among the columns of A. It's a little bit row versus column, but so this is what a matroid is, and the result of these people is that the result of these people that I mentioned is the tropical variety is determined by the matroid, and in fact only the matroid. It sees a matroid and only the matroid, meaning that if you have two linear spaces that has the same tropicalization, then they have the same matroid. Yeah. So what is a matroid? Or matroids are also called combinatorial geometry. It's the axiomatization of independent structure in combinatorial recent algebra. So two main examples come from graph theory and linear algebra. So in graph theory, this is a graph, and then I'm looking at the edges. So it's like a matroid theory. It's like doing graph theory without vertices. You're not allowed to talk about vertices, okay? You're only allowed to talk about edges. So right here we say that a collection of edges is independent if there are no cycles, right? So that means that 1, 2, 4 is dependent, but 1, 2, 5 is independent. Right. On the other hand, right here, I have 6 points in R2, or I can think about I can point, comb on them, and I can think of like 6 vectors in R3. I have like my origin somewhere outside the board. I have 6 vectors in R3, and I can talk about linear independence among those 6 vectors, right? So right here, in this case, I have my 1, 2, 4. These are linearly dependent, right? So you can check that the independent structure here and independent structures here are exactly the same. Okay, so it is this abstract information about the independent structure is the matroid. So this is the spirit of doing geometry without geometry, right? You can you're secretly thinking about these combinatorial geometry without actually having those vectors or vector spaces, right? So here's a definition is really simple. So a matroid is a finite set together with a subset called the basis or maximum independent set that satisfies the so-called basis exchange axiom. So you can check that it is true for graphs and vectors. So if I have 2 bases of a vector space, for example, if I have one vector that is in one base but not in other, then you can swap it out. You can remove it and then replace it with another vector in a different basis. And that is true for spanning trees in a connected graph, which are bases as well. If you have a spanning tree, and then you can remove an edge, and then you can replace it with another edge in a different spanning tree, right? To get a new spanning tree. Right? So put a little bit of a geometry back into geometry. This is something that Raman will like because polytopo, right? So I can think of, like, for example, I have 4 vectors that are pairwise linearly independent in R2, right? So it has 6 bases. So all pairs, they form bases, right? So you can see that, you can draw this picture. I can think of this is a picture that is living in R4. So 1, 2, meaning I looking at the vector. 1, 1, 0, 1, 4 is the vector, 1, 0, 0, 1, and so on, right? So these are 6 points in R4, and this is their convex form. And then you can see the basis exchange axiom. So if you take two bases, and if you want to swap out one, and then if you want to be able to swap out and like get closer to the other one, right? So then if you can replace 1 with 2, so you can go to here that get closer to the 2, 4. So these basis exchange axioms says that if you look at this object called the matroid-based polytope, then these edges in this polytope are in the directions ei minus ej's. So in this case, this edge, right, is in the direction, right, E2 minus E1. Yeah. So similarly, if you look at this configurations of 4 vectors, right now 3, 4 is no longer the base. So now I have this picture, matroid-based polytope, and then the edges are still in ei minus ej directions. But if you look at this picture right here, this is no longer the basis of a matroid. For example, if you look at 1, 3, and 2, 4, there is no way to swap 1 out of A, right, by anything in B, because if you replace 1 with 2, you don't get a base. And if you replace 1 with 4, you also don't get a base, right? And you can also see, like, in this polytope where this edge is not in the direction ei minus ej. Okay. So that is the combinatorial abstraction of linear independence. And then you can ask, here's a representability problem over a chosen field. If you're given a matrix, so if you're given a collection of potential bases or independent sets, can you realize the situation by actual represent the situation by linear independence among collection of vectors in k to the n? Yeah. And you cannot always do that. So for example, if you look at these 7 points, you can think of them as f2 to the 3, remove the origin, right? So while these are obviously vectors over f2, but this linear independent structure cannot be represented over real numbers, for example. Okay, so right here, these are linearly dependent sets, right, over f2, and then this circle denotes that these 3 points are linearly dependent. Okay, so R2 over real numbers, you cannot get this picture. So it's not representable over R, but it is representable over f2. But there's this, look at this Varmush matrix. So this is a matrix, so the red dots are the elements, so there are 8 elements. And then this plane signifies that these 4 elements are dependent. Okay, these 4 elements are dependent, but there is no plane between these 4 elements right here, because these are independent. Okay, so it turns out that this collection of independence satisfies the base exchange axiom. But you can see in this picture, right, I cannot realize this without having these 4 actually lying on the plane. Okay, if you actually try to construct them, these 4 points are forced to be on a plane. So that's why this matrix is not representable over any field. There's another example is the non-purpose matrix. So Purpose theorem says that if you have this configuration on the right, then these 3 points x, y, z have to lie on a line. But you can just take this structure and you can just declare x, y, z, you're now free, you're now independent, right? This still satisfies the base exchange axiom, but it violates the Purpose theorem, therefore it's not representable over any field. So there has been a long history of people trying to axiomatize this representability over a field. So in 1978, Varmush wrote a paper that makes an axiom of matrix theory is lost forever. He proved that you cannot axiomatize using first order logic, using finitely many statements in first order logic representability. And then in 2012, these people came out and said that, come on, first order logic is too restrictive. Let's enlarge the language a little bit. Okay, and then they make a conjecture that it is actually also not axiomatizable with a second order logic with a question mark. And then they proved that their conjecture in 2018. Okay, so now we know that it cannot be done in second order logic. Of course, if you allow more, if you allow linear independence in your language, then of course you can do it, right? Yeah, but you cannot do it with like sort of simple statements. All right, so matrix representability is a hard problem. And also I like to mention the Munoz universality. It says that it's not just representability, but it wants to look at realization spaces, right? So you want to see like, given a matrix, what are all the configurations of vectors that realize your matrix, right? So for example, if your matrix is rank R on n elements, so you're looking for n by R matrices, right? And then where the linear independence amongst the columns give you the matrix that you want. So basically you're asking for, whether this collection of determinants, right? Linear independence is seen by the determinant. Whether collection of determinants, vanishing conditions, right? You specify which determinants has to be 0 and which determinant has to be non-zero, whether this collection has a solution, right? So yeah, so Dante knows a lot about it. He was telling me cool stuff yesterday. So Munoz universality says that every real semi-algebraic set defined over Z is basically realized as a realization space of an oriented matrix or a convex polytope. So in other words, implication is that these realization spaces can be arbitrarily bad. In particular, they can have arbitrarily bad singularities because everything is a realization space of a matrix, basically. That's what universality means, right? Everything is a realization space. So this is what Ravi Fakir called the Murphy's law in algebraic geometry. Things can be as bad as you want, right? Deformation spaces can be as bad as you want. And also another implication is that over rational numbers, right? Checking realizability is checking whether, a system of equations or inequations have a solution, and this is the Diophantine equation over rational numbers, and it is unknown whether that is decidable, right? It's not that we don't know it's undecidable, it's even worse. Okay, we don't know if it is decidable or not, right? So matroid representability is pretty high. Any questions so far? Yeah. Over the real, it is decidable because by the quantifier elimination. So you can write down this equation inequality whether they exist. So that is like at least like theoretically it's decidable, but in practice though it'd be pretty difficult. Yeah. All right. So now I want to look at another object that we may want to look through tropical lens in a couple of minutes. So these are Grassmannians. So we're looking at moving on from, instead of looking at a single linear space, we want to look at the set of all linear spaces, right, of a fixed dimension D, in k to the n, where k is some field, right? So how do we write down a linear space? Of course, you can write down a linear space as a row space of a matrix, but this coordinate isn't so good because there are many choices of this matrix give you the same row space, right? You can do row operations that give you the same row space. But one thing that you can do is you can take this matrix and you can remember all the, right, in this case, 2 by 2 minus, determinant of 2 by 2 submatrices. In this case, there are 6 of them, right? So this 1, 2 meaning that I take this 2 by 2 minus, right? So 1, 4 meaning that I take this 2 by 2 minus, and so on. All right, so I take these 6 numbers, and then if I do row operations, all these 6 numbers, they change together. The only way that they can change is that they all get scaled by the same number. Right? If you do the elementary row operations. So that means that these 6 numbers, modulo scaling, right, is a good coordinate for to remember the row space. So this is called the Plücker coordinate. So these are the Plücker coordinates of this linear space, and this is called the Plücker embedding. So I take a linear space, and then I remember the d by d minus of this d by n matrix, right? Okay. So let's see. So recall the matroid of this linear space is linear independence among the columns, and linear independence among the columns are seen by the zero pattern of this d by d minus, right? Because 2 by 2 right here, 2, 3, right? This coordinate, this Plücker coordinate is 0. That means that these 2 vectors are linearly dependent, right? And then every other pair is linearly independent because these are non-zero, right? So that means a 0 pattern of Plücker coordinates is the matroid, gives you the matroid. And tropical variety sees the 0 patterns. So that means that the tropicalization of the Grassmannian sees all the matroids representable over the given field, right? Okay. So this kind of tells you that tropical Grassmannian is a complicated object, right? So I've tried to convince you that matroid representability is a complicated problem, and tropical variety sees that. So tropical variety is some kind of complicated polyhedral object. Okay. Now another move on. So I'm going to, before I introduce tropical varieties using log limits, because I find this intuitive, but I want to show you another way to tropicalize without limit, which is a little easier. As I said, amoebas are pretty cool, but they are also really hard to compute with. Right? So right here, instead of looking at log base t where t goes to infinity, I'm going to think of t as a formal variable. Right? So and then I'm going to enlarge the field and look at the Poisson series field. So these are like the formal power series where the fractional exponents. And I put the negative one because I'm thinking of like field as it starts from some term and then the exponents go down to a negative infinity. Okay. And then there is a valuation map that takes a series to its largest exponents. Instead of the smallest, there is the maximum min choice. Yes, okay. I'm sorry, Kevin. Yeah. So, Right, so you should think of it as like when t goes to infinity, this valuation is doing two things at once. It's taking the logarithm, right, and the limit as t goes to infinity, right? So we're doing the limit without taking limits. Okay? Yeah. So then tropicalization is defined as the set. Actually, I should put like Euclidean closure. Yeah. So I should put a little bit of closure, Euclidean closure of the set of valuations. So another nice thing about this definition is that now you are no longer tied to this sort of having logarithm and complex absolute value. You can start with any field with valuation, non-Archimedean valuation, like for example, periodic fields that I heard a lot of people in Frankfurt are interested in, right? So you can tropicalize with other valuations as well. All right, so the point is, say, if you have a something algebraic or semi-algebraic, on one hand, you can take the log limit set and get the tropical object. On the other hand, you can enlarge your field a bit, right? You can go into a value field, a field with valuation, right? You use the same equation and inequality that define your object. So you just consider those equation and inequality over the larger field, and then you take the valuation. You get the same object without having to take limits. Yeah? Let's apply this point of view to an earlier example. So recall we have seen this example before, right? We looked at the amoebas, and then we have this. Now, this equation, instead of looking at this t as an actual parameter, like a real number, we're going to think of t as a formal, right? Formal element of my coefficient field. Right? Now, t is now over some Poisson series. Now, I'm looking at this equation, and I'm asking, okay, what are the series x and y, right, that satisfy this? So a necessary condition, right, a natural necessary condition is that for x, y, these are x and y are both series. To be a solution, after you plug them in, the highest degree terms must cancel. Of course, everything must cancel. In particular, highest degree terms must cancel, right? So, well, what are the highest degree terms? Highest degree term here has valuation 1, right? Highest degree terms here has valuation 2 plus valuation of x, right? So x squared has valuation 2 times valuation of x, and so on. So these 6 terms has these 6 valuation, and for them to cancel, right, maximum of these have to be attained at least twice. Otherwise, if you look at, like, if I'm adding 6 series, and if the maximum is unique, there will be no cancellation. So there has to be at least twice. And if you write this down, right, if you write this equation, there's a bunch of linear equations, inequality. You can do like the cases, maybe these two, maybe those two, and so on. Okay, you can, if you mess around with this, you will get this picture. The advantage is that you don't need to work with amoeba, or you don't need to take limit, you don't need to take logarithm, right? So it is more combinatorial. There is even a nicer way that goes through the Newton polytope and subdivisions, but I won't go through it. All right, now we apply this point of view to the Grassmannian, right? So the point here is that if you have a usual equation, tropicalizing the equation gives you something about max attained twice. Right, now we're going to apply this point of view to the Grassmannian, right? So let's go back to the Grassmannian 2,4. So it has, in the Plücker coordinate, it has 6 coordinates, and then it has they satisfy this equation. Yeah, so this is like 1, 2 minor, and 3, 4 minor, and so on, right? So these minor satisfy this relation, and then using the same logic as before, that means that their valuation has to satisfy this so-called tropical quadratic Plücker relation. That maximum has to be attained at least twice. Right. Okay. So let's try to understand this a bit better. What does it, how do I visualize these maximum attained twice? So these 6 Plücker coordinates are naturally associated with the 6 vertices of this octahedron. And then maximum attained twice, maybe the maximum is attained at, right? So each of these 3 terms correspond to the 3 diagonals of my octahedron. Yeah, 3 diagonals, right? Like this, that connect the opposite vertices. So right here, the first picture is showing the situation where these 2 diagonal maximum is attained twice right here, right? So and bigger than this one. So what you should be thinking about is you have this polytope, and then you take these points and you pick them up and raise them to a next dimension, given where the height are these numbers, right? The heights are given by these 6 numbers, okay? So, and then this, what is the value of this? It is 2 times the height of the midpoint, right? Okay, if I divide it by 2, that is the average, right? So that means that I'm comparing the height of the, these 3, the midpoint of those 3 diagonals. Where do they go? And maximum attained twice, meaning that, well, 2 of them are maximum and 1 is lower. That means if I'm looking from above, if I raise this and put it to higher dimension, if I look from the above, right, I have to see 2 of the diagonals like flat together on a square, and the other one maybe below. So that means if I'm looking from above, I don't see any of the diagonals because they are flat. 2 of them are flat together. So if I see from above, I may see one of the pink squares that I draw, but I don't see a diagonal. So in other words, the upper convex hull is edge in the direction EI minus EJ. So this condition we have seen before is a matroidal condition, right? It's the being matroid. Yeah, any questions? All right, so we're going to take a visual break. Look at this, my favorite Christmas ornaments. It's called pavuk, or spiders, introduced to me by my Ukrainian husband. So yeah, there is a lot of polytopes there. Okay, any questions? It's not mine, we didn't make it. I found it on the internet. Yeah. All right, so a little bit of a recap. So we have the situation where, we have in the classical world, right, we have linear spaces, and the collection of linear spaces form a Grassmannian. If you tropicalize it, the tropicalization map turns linear spaces into matroids. So now you have tropical Grassmannian. It's a collection of matroids. Valuated means that when you take the minors of this d by d minor, you remember the valuations as well as whether they're 0 or not. Okay. And then by construction, they're all representable. But of course, they are matroids that are not representable that I've shown you, those Vamosh and non-purpose and so on, right? They are non-representable things that are out there. Okay, so they also live in the tropical world and in this set, what is called the Dressian. So in the world of all valuated matroid. So, and then this is defined by the tropical Plücke relations that we saw earlier. This maximum attained twice thing. Yeah, so for the background, so I'm going to introduce just one more space that is a friend of the Grassmannian. These are called flag varieties, right? So Grassmannians, remember, these are the set of linear spaces, right? Linear subspaces of a vector space. A flag means that it's a chain of linear spaces, right, of all dimensions. This is a complete flag variety. So it is a 0 in a line, in a plane, and so on, right, all the way up to Kn. So it's a flag of linear spaces. And then the set of all flags, it forms an algebraic variety. Well, how do you give it a coordinate? How do you write down a flag? One way to write down a flag is to write down an n by n matrix, where the first row span the line, right? And then the first 2 rows span the plane, the first 3 rows span the 3 plane, and so on. One way to write down a flag is by this n by n matrix. And then you can remember from the n by n matrix, you can remember the Plücke coordinates of just the first row only, or the first 2 rows, or the first 3 rows, and so on, right? So what you remember is that, you get a map from all the subsets of an element set to the ground field, where for a set, you look at the determinant of the matrix, where you look at the top justify, right, I by I minor. So meaning that you look at when I is equal to 2, then you look at the top 2 rows, and then you look at some, right, 2 columns of the top 2 rows. You look at the top justify minors of this matrix, and they give you something like the Plücke coordinate for the complete flag variety. Right? And then similarly, you have a flag, and then you can tropicalize to this tropical flag, and you can think of a chain of valuated matrices, or you can think of chains of tropical linear spaces with some incidence relation. Like you can write them down as like this max attained twice thing, right? And then you can also have a representable chain of valuated matrix versus everything else out there called the flag Dressian. Yeah. All right. Now I'm going to start talking about going toward the new stuff, okay? So about principal minors. So it's like complete change of topic for now. So if you have a square matrix, n by n matrix, and then you have a subset of the index set, right? AS is the determinant of a principal submatrix. Means if I have a subset and I pick up the same collection of rows and same collection of columns, right? So I have a matrix, a submatrix, and I take the determinant. That is called the principal minor. And the principal minor map is it inputs a matrix, a square matrix, and it outputs the collection of principal minors. Right? So it's a map from a low dimensional space to a high dimensional space. Okay. Later on, we're going to compose with the tropicalization map or the valuation map and look at the valuation of the principal minors. Right? So this is something that people have studied a lot. There is something called principal minor assignment problem in matrix analysis, where the problem is to characterize the image of the principal minor map. Right? So which collection of these 2 to the n numbers show up as principal minor of a single matrix, right, altogether. In other words, what are the relations, equations, and inequalities among the principal minors? There are many variations of these problems. Of course, they are like symmetric, skew symmetric, general, positive, definite, not, general, over which field, over which ring. There are many variations. So I just mentioned a few related results. Well, of course, in numerical linear algebra, people will actually be interested in actually computing it, right? Given some 2 to the n numbers, or maybe some collection of them, you want to actually reconstruct the n by n matrix that they come from. Right? So some relevant results are for symmetric matrices, for general symmetric matrices over real or complex numbers. So this was solved by Luke Erdin, based on the conjectures of Horst and Stromfors. And then this result was extended to arbitrary Unix factorization domain by my collaborators, Abir and Cynthia, recently. So our setting is sort of inspired by this work, but we're looking at a more restricted but very important family of matrices called positive definite matrices. So they were looking at all symmetric matrices, right? So we want to look at positive definite matrices. So we want to look at the tropicalization of the image of the principal minor map, right, on the positive definite matrices. Let me remind you, a Hermitian matrix over complex number is called positive definite. If any of these 3 equivalent relations are satisfied, all principal minors are positive, or eigenvalues are positive, or it could be factor B adjoint times B, where B is invertible. Otherwise, you get, if you don't have this extra condition, you have positive semi-definite. Okay. So it is well known that if you have an n by n positive definite matrices, then the map that takes the index set to the logarithm of the principal minor, log principal minor map, it is submodular. Submodular means that it satisfies the submodularity equation. So you can think of this as this is also shows up in matrix theory, like matrix rank function satisfy this. People in economics study a lot, so this means that this is the diminishing marginal return inequality. Okay, so if you move things around, so if I move right, so if I move this to the left, if I move this to the right, so this means that if I already have a lot of things, I am less, my valuation of the extra things that you have, like diminishes. So this is the diminishing marginal return. So it shows up in economics a lot. Yeah. So log principal minors are submodular. And then what tropicalization is the log limit. Okay, so if you take the limit, it is still submodular. Okay, like the set of all submodular functions is a polyhedral cone. Right? These are finitely many linear inequalities. So it's a polyhedral cone. It's a closed polyhedral cone. Taking the limit doesn't leave the cone. Right? So we know that this tropicalization lives inside the submodular cone. Yeah. Now let's look at the valuations, right? So let's forget about the log limit now. So we're going to look at the valuation, but does it make sense? Yeah, so we have to extend real numbers to real Poisson series. I'm going to denote with this R. And then we extend the complex numbers to the complex Poisson series. And then you can think of a complex Poisson series at like real Poisson series plus, this is square root of -1 times a real Poisson series, right? So that means you have complex conjugation as well. So you can talk about Hermitian matrices. And then you can talk about positivity. We say that a real Poisson series is positive if leading coefficient is positive. The intuition is that I'm thinking of this T as like really, really large, right? When T is really large, the only thing that matters is the leading term. If the leading term is positive, then the series is going to be positive. So it makes sense to talk about like all this. Makes sense to talk about positive definite, makes sense to talk about principal minus being positive or eigenvalues being positive or being able to factor, right? All these things make sense over real and complex Witten series. So let's look at a specific example. So now I have this B, and then I have my B transpose B. I don't have complex numbers, so I don't need to complex conjugate anything. Okay, so A is a positive definite, and I have computed for you. These are the principal minus, and these are the valuation. And you can check that this is a submodular function. Yeah, so for example, you know, if S and T are, let's say, like 2 and 3, then, right, so on the left, I have 2 plus 6 is 8. Right, on the right, I have the union plus the intersection, it is 6. Okay, so 8 is bigger than equal to 6, right? So you can do all these checks, and this is submodular. But here is something actually stronger than submodular. In fact, you can see that in the cube right here, so I draw the cube because, you know, these subsets are, of course, naturally corresponding to the vertices of the cube. Inside the cube, I have an octahedron hidden in there. Okay, if I chop off 2 opposite corners, I have an octahedron, right? And then in this octahedron, I have this maximum attained twice for the 3 diagonals. Yeah, so I have my 6, 6, 0, 0, and I have the 2, 2, right? So the diagonals are 6, 4, and 6, right? So that means the maximum is attained twice. You can also observe that this implies the edges in the upper convex hull are in EI minus EJ directions or plus or minus EI directions, which are the original cube directions. Okay, so we have that. So this condition is called M natural concavity. And it turns out that this is always true. And then it is well known that this condition implies a submodularity. So this is something stronger than submodularity. So it follows from a result of Brendan on stable polynomials. If you tropicalize principal minus, so n by n positive definite matrices, you get an M natural concave function. So if some of you might have seen M concave function at this conference, and then so M concave function means the upper convex hulls are in direction EI minus EJ. M natural concave is sort of you just like dehomogenize, you project down one variable, right? So instead of looking at the edges in direction EI minus EJ, now you have EI minus EJ and the EIs, but you lost a variable. Right? These are me and my kids. All right, so our question is, so now summary. What we know is that this tropicalization of principal minus of positive definite matrices, they live inside the M natural concave function, which in turn live inside the submodular function, right? Because this inequality is known to be strict by sort of dimension count. Submodular functions are full dimensional object, and M concave functions are not full dimensional object. It's well known. How about this one? So when we started working on this project, we don't know actually. We didn't know whether this containment is strict or not. So our question was, right, do we get some kind of representability of the principal minus? Okay, are we getting some kind of representable M natural concave function? And what does that even mean, right? What does it even mean? So to be honest, that was like taking us a long time to sort out what does it even mean to be representable. So now here is what we came up with. So now without representability yet. So these are different ways to understand M natural concave function. So one way is that on a cube, okay, on a cube. One way is that if you look at this like lift into the next dimension and looking at the upper convex hull and edge direction, the edge directions are in the you know the cube directions or these sort of matrix directions. So this is one definition of M natural concave function. And that turns out that it's equivalent to looking at the multisymmetric lift, meaning that if you have a function from right on the cube, you can lift it to a function on a bigger set. So these are all the n element subset of a 2n element, right? So we're saying that you input an n element subset. My output is my function value, my original function value, right? I only care about how t meets the first n, first n element. I don't really care about the last. So in other words, I just throw in extra elements to turn it into an n element. So it's kind of like homogenization, right? So right here, all these subsets have all different sizes. Now I make them all to be size n. Right? So I have this set on this bigger, a function on this bigger set, this multisymmetric, right? It belongs to the Dressian. Dressian, remember, is the set of all valuated matroid, the set of all matroid, the set of these geometry without geometries. Okay, so they satisfy these tropical quadratic Plücker relation, these max attained twice thing. So it is equivalent. Another way to characterize M natural concave function is that F is submodular and that belongs to the flag Dressian. Right? So this is again the combinatorial model for the flag variety. So these are like combinatorial statements, that all these are equivalent. A nice thing about, right, this is where we started with, it's not obvious what representability means. But right here, we know what representability for the Dressian is. Dressian is the, it's the collection of evaluated matrices. So we're saying that do the matrices that show up, are they representable? And then right here, we know what representability is. We have these like sort of flag of tropical linear spaces. Do they come from an natural linear spaces, classical linear spaces? We have representability over there too, right? So a priori, these two representability may be different. So our main result is that in fact, they turned out to be equal, which was not actually what we were expecting, but it turns out to be very nice. We were very pleased to find that these three notions of representabilities are equivalent, right? One is that F belongs to tropicalization of principal minors of the positive definite matrices, right? The second is that if you do the multisymmetric lifts, it is representable as a, right, as a evaluated matrix of some linear space, n-dimensional linear space in 2n dimension. And the third one is that it is representable as a flag, tropicalization of a flag of linear spaces. So it turns out that these three are equivalent. Yeah. So it could also like a little bit of a negative result in the sense that at first we're hoping that, oh, maybe this tropicalization of principal minor is like pretty nice. We can like describe it. But right here, this shows us that it is pretty complicated, right? So I've spent some time trying to convince you that representability is a hard problem, and the Grassmannians and flag varieties are very complicated objects because they know about, all these representable matrices. So this indicates that these principal minors, tropicalized principal minor problem is very difficult, right? Because as difficult as testing representability of flags, which is very difficult, right? So it is kind of a hardness result. All right, so if I can have like 1 more minute, I'll tell you about maybe, you're like, okay, fine, the tropical results, whatever, maybe you don't care about tropical geometry. Let me go back to the classical world, right? What does tropicalization tell us about our original set, original principal minor? Can I tell you something that you didn't already know about principal minor or positive definite matrices, right? So it turns out the tropicalization in the real case, it's good for finding inequalities for semi-definites, a semi-algebraic set. So we have something called the Lifton lemma. It says that for a semi-algebraic set, if you have a tropical inequality that is valid on your tropicalization, it could be lifted to the usual classical algebraic inequality valid on my original set. In other words, tropicalization sees all the monomial supports and valuations and signs of all polynomial inequalities that is valid on the set. I like to think of it, tropicalization knows about the shape of all the inequalities, or the combinatorial shape of all inequalities. But where, what are some of the tropical inequalities satisfied by our principal minors? All right, so here are some. We know that from the M natural concavity, we see that maximum is attained twice, okay? So these little a's are the valuations of the principal minors, right? So I can translate this max attained twice into 3 inequalities, okay? Yeah. And then each of these is a tropical inequality. Lifton lemma says that, for example, I take the first inequality, I should be able to lift it to the usual inequality of the form, of the same form. So right here, maximum of these is bigger than or equal to this, means that there has to be an inequality of some positive number times, A1, A2, 3. So this plus this is a tropical multiplication If you lift them, you get usual multiplication, right? Maximum is the plus, right? So there has to be inequality like this, and we were able to prove that actually very nice inequality that very simple, but we were not able to find in literature, so it may actually be new, right? That is sort of inspired by our study in tropical geometry, and there are many more inequalities waiting to be discovered from our tropical geometry. All right, so here's a summary. You walked out of here and your friend asked you what was the talk about and you've been sleeping. Here's your cheat sheet, okay? So the take-home message is the tropicalizations of varieties and semi-algebraic sets. They help you reveal combinatorial and matroidal structures. In this principal minors, without tropical geometry, you would not have seen the matroid. You need the tropical geometry to see the matroids in there. And it allows you to find monomial supports of inequality. And in this talk, we apply this to the principal minors of positive definite matrices. So thank you. I ended with this pavuk in my house. And then this is somewhere in Ukraine. Okay.